All right, everybody, buckle up. We're diving headfirst into the wild world of number theory today.
Yeah. Get ready to explore the fascinating hidden patterns in the fabric of numbers.
We'll be using the number theory section from the Sympy documentation as our guide.
It's going to be our treasure map today, leading us through all the cool tools and techniques mathematicians use to unlock the mysteries of numbers, so to speak.
It's our mission today to make sure you walk away with a good grasp on all these core number theory concepts.
And hey, you might just learn some new party tricks for your next trivia night.
Exactly, you never know. Okay, so let's kick things off with the essentials. Prime numbers.
The building blocks, right.
Right. Now, Sympy has this very handy function called primeth. Basically, you give it a number, let's say 10.
And it'll spit out the 10th prime number.
Which is 29th.
Exactly. What's really cool about this function, though, is how efficient it is. It uses some pretty clever math.
Like what?
Like the prime counting function, just to give you an example, to quickly pinpoint those prime numbers, even when you're dealing with really massive numbers.
The prime counting function, huh? Is that like taking a census of all the prime numbers or something?
You got it. It tells you how many prime numbers exist up to a specific number. So say you wanted to find the millionth prime number.
Okay.
Instead of having to check every single number, this prime counting function lets mathematicians estimate where that prime number roughly sits on the number line.
Ah, so it's like a shortcut through a giant jumble of numbers.
Exactly. And since we're talking about shortcuts, we should probably mention prime gaps, too.
Oh, yeah, prime gaps.
And just so everyone's on the same page, these gaps, they're not really empty spaces. They represent the differences between consecutive prime numbers, and they're actually full of all sorts of little mysteries that have kept mathematicians busy for centuries trying to figure them out.
Like that twin prime conjecture, that one always makes my brain do a few backflips.
Right, that's the one that says there are infinitely many pairs of prime numbers that are only 2 apart.
Like 3 and 5 or 11 and 13.
Exactly. Seems pretty straightforward at first glance.
Yeah.
But actually proving it is a completely different story.
Yeah, I bet.
And it's those deceptively simple questions that make number theory so fascinating. Take Goldbach's conjecture, for instance. It claims that every even number larger than 2 can be written as the sum of 2 prime numbers.
So like 10 is just 3 plus 7, and 24 would be 11 plus 13. But proving that holds true for every single even number, I can see how that would be a real head-scratcher.
It's a real challenge. And what's interesting is that both of these conjectures, even after centuries of mathematicians trying to crack the code, they still haven't been proven.
Wow.
It really highlights that intriguing dance between simplicity and complexity that lies at the very heart of number theory.
It's like the more we uncover about numbers, the more we realize just how much more there is to discover.
Exactly. And Sympy actually gives us a pretty handy tool to help us break those numbers down and uncover their prime factors.
You mean the factor-in function?
That's the one. It's like having a magnifying glass for integers, allowing you to see all those prime building blocks.
I like it.
You just input any whole number, and bam, this function gives you this neat little dictionary showing you exactly which prime numbers, when multiplied together, will give you back your original number.
So it's like reverse engineering numbers, taking them apart to see what they're made of at the most basic level.
Exactly. And here's the really cool part. There's this thing called the limit parameter that lets you set a kind of budget for your factorization.
A budget.
Yeah. Let's say you're only interested in factors below 100, for example. You just set that limit to 100, and the function won't even bother searching for any factors beyond that point.
That's gotta be super useful, especially when you're working with those mega huge numbers where finding every single prime factor could take forever.
For sure. It's all about setting some boundaries for your exploration.
Love it.
And for those who prefer a more visual approach to understanding things, Sympy also has this visual option built into the function.
Oh, nice.
It presents the whole factorization in a much more engaging way, making it a lot easier to grasp those relationships between the numbers and their prime factors.
Yeah, because who doesn't love a good visual, right? It's like taking those abstract number relationships and turning them into something you can actually see and interact with.
Exactly. Now, speaking of relationships, the Sympy documentation also dives into this cool concept called smoothness.
Smoothness. Okay, now you've piqued my curiosity. Are we talking about some smooth jazz here, or what?
Not quite, though I do love a good analogy. In the world of number theory, smoothness refers to the size of the prime factors a number has. Think of it this way. A number that can be broken down into many smaller prime factors that's considered smoother than a number that has only a few larger prime factors.
So it's not really about how smooth a number feels, but more about how easily it breaks down into smaller chunks.
You got it. And Sympy actually gives you a way to measure that smoothness with the smoothness pribe function. It not only tells you how smooth a number is, but also how smooth its neighbors on the number line are.
Its neighbors, how does that work?
Well, that's where things get really interesting. Knowing the smoothness of the numbers surrounding a potential factor can actually be incredibly useful, especially for those more advanced factoring techniques. It's a bit like having a map that shows you the lay of the land around a potential factor, helping mathematicians navigate those vast landscapes of numbers a bit more effectively.
That's fascinating. So we've explored prime numbers, the gaps between them, and even how to dissect them and see what they're made of. Now, what about those numbers that fit nice and neatly inside other numbers?
You're talking about divisors.
Divisors, exactly.
Those are fascinating characters in the world of number theory. Might seem pretty straightforward at first glance, but trust me.
There's more to it, isn't there?
Oh, yeah. There's definitely more to them than meets the eye.
So there's more to divisors than meets the eye. I'm all ears.
Oh, yeah. They're more nuanced than you might think. We've got different types, each with their own unique quirks.
Okay, you're making me think of divisors as having different personalities now.
Well, we've got the regular divisors. Those are the ones that divide evenly into a number, including 1 and the number itself.
Okay, so for 12, that would be like 1, 2, 3, 4, 6, and 12.
Perfect example. Then we've got the proper divisors. Those are similar, but a little more exclusive. They don't include the number itself.
So no 12 in that case.
Exactly. Just 1, 2, 3, 4, and 6. Then things get even more interesting with unitary divisors.
Unitary divisors are what makes them stand out?
Well, these are the independent types. They don't like to share prime factors with the original number, other than 1, of course.
So they want their prime factors all to themselves. Can you give me an example?
Well, let's take 24. Its unitary divisors would be 1 and 24, because 24, if you break it down, has those prime factors of 2 and 3, right?
Yeah, 2 times 3.
Exactly. But 1 and 24, they don't share any of those prime factors, making them the independent unitary divisors in this case.
Ah, I see. It's not just about dividing evenly, it's also about the relationship between their prime factors, like a whole hidden layer of complexity.
That's it. And then we have the rebels of the divisor world, anti-divisors.
Anti-divisors. Okay, I'm really intrigued now. What makes them so rebellious?
These are the ones that don't care about dividing cleanly. Instead, they want to leave the biggest remainder possible.
The troublemakers.
They like to shake things up a bit. For example, if we take the number 10, an anti-divisor would be 3.
Because 10 divided by 3 gives you a remainder of 1.
Exactly. And you can't get a larger remainder when dividing 10 by any number bigger than 1.
Okay, that makes sense. So we've got all these different flavors of divisors. What's the point of classifying them this way? Why does it matter?
That's the key question. You see, these seemingly basic concepts of divisors, especially when we start getting into prime divisors, they have huge GE implications in different fields, like cryptography.
Cryptography, like codes and cybersecurity and all that?
Exactly. A lot of the security of our online transactions. It hinges on the fact that factoring large numbers into their prime divisors is a really, really tough computational problem.
Wow. So all these different kinds of divisors, they're not just mathematical curiosities. They actually impact our everyday lives.
Big time. And that leads us to a pretty cool function that a brilliant mind like Euler was particularly interested in.
Euler. Okay, now we're talking. Whenever Euler's name comes up, I know things are about to get fascinating.
Right. He came up with what we call Euler's totient function.
Okay.
Often represented as, get ready for this.
All right, I've got my notes ready.
So this function tells us how many positive integers are less than or equal to a given number, which we'll call n, and are relatively prime to n.
Relatively prime. Can you remind us what that means again?
Of course. Two numbers are considered relatively prime, or coprime, if their greatest common divisor is 1. Basically, they don't share any common divisors other than 1.
So 8 and 15 would be relatively prime because their only common divisor is 1. But 6 and 9 wouldn't be because they share a common divisor of 3.
Exactly. You got it. So essentially, Euler's totient function helps us count up all those coprime buddies that a number has.
I like that coprime buddies. It's like a popularity contest for numbers, seeing how many other numbers they get along with in that special coprime way.
That's a great way to think about it. And, just like we were talking about with divisors, this seemingly simple concept has some pretty deep connections to various areas of mathematics and beyond.
It's mind-blowing to me how these fundamental concepts like primes, divisors, Euler's function, it's all interconnected.
It really is. And believe it or not, we're just scratching the surface here. Sympy actually offers even more advanced functions that take us even deeper into the rabbit hole of number theory.
Deeper, huh? All right, I'm ready. Let's go. What other tricks does Sympy have up its sleeve? Hit me with those advanced functions. I'm ready for anything.
All right, well, get ready to enter the world of modular arithmetic with a function called norder, AN.
Modular arithmetic. That sounds a little intimidating, not gonna lie.
It's not as complicated as it might sound. Think of it like a clock. But instead of hours, we're dealing with remainders after we divide numbers.
Okay, I think I'm following.
So, for example, on a clock, 13 hours is the same as 1 hour because we only really care about that remainder after dividing by 12, right?
Right.
So basically, this norder AN function helps us figure out how many times we need to multiply a number A by itself before we end up with a remainder of 1 when we divide by another number.
So we're basically figuring out how many steps it takes for a number to circle back to 1 in this modular world.
That's a great way to put it. And this whole idea of order ties into another really interesting concept, primitive roots.
Primitive roots, what are those all about?
Imagine you have this master key, right?
Okay.
And this key can unlock all the other numbers within a specific modular system. That's kind of what a primitive root is like. It's this special number that when you raise it to different powers, it can actually generate all the other numbers that are relatively prime to a given number.
So it's like the VIP of the modular world gets access to everything.
You got it. And of course, Sympy has a function for finding these primitive roots too. Primitive root.
Of course it does.
But there's a catch. It only works for prime numbers. But it just goes to show how connected all of these concepts are, even when we start dealing with the more, I guess you could say, advanced stuff.
It's amazing how the more we dig into this world of numbers, the more interconnected it all turns out to be.
It really is. And speaking of digging deeper, we also have functions like squart mod, A, cap T, AP. This one helps us solve something called a modular congruence.
Okay, gotta be honest, modular congruence definitely sounds like something straight out of a science fiction movie.
I promise it's not that scary. Just think of it like a regular equation, but with that added modular twist we've been talking about.
So instead of finding solutions that work for whole numbers, we're trying to find solutions that work within a specific modulo.
Exactly. And what's really cool is that these might seem like very abstract equations and concepts, but they have real-world applications.
Oh yeah, like what?
Well, for example, these concepts are actually used in a lot of cryptographic systems.
No way.
Yep. The ones that keep all those online transactions we were talking about earlier safe and secure.
It's incredible how these seemingly abstract mathematical ideas, things that people have been thinking about for centuries, actually have such a huge impact on our lives today.
It really is remarkable.
This has been an amazing deep dive. We started with prime numbers, those fundamental building blocks of all numbers, and now we're talking about cryptography and the security of the entire internet.
It's been a wild ride. It just goes to show the power of number theory and how those hidden patterns within numbers shape our world in ways we might not even realize.
It makes you wonder what other secrets are still out there, hidden within the fabric of numbers, just waiting to be discovered, right?
Absolutely. That's the beauty of it. There's always more to explore.
Well, on that note, we'll wrap up this deep dive into number theory. Thanks for joining us, and until next time, keep those numerical curiosities alive.